Okay, example 119. It says, suppose that after taking a random sample of airline passengers, we have the following data. N is 36, X bar is 200 pounds. The standard deviation known from a previous study is 33.3. It says, use the central limit theorem, the null hypothesis from above, and the data above to create a test stat that has a Z distribution. Okay, so first thing I want to do is to copy down the hypotheses that we had in the previous examples. So we had a claim in the problem, and the claim said essentially that the mean was going to be greater than 185 pounds. And then we had a pair of competing hypotheses, HO and HA, and we saw that because of this symbol, the claim and HA in this case were the same. And then we had the opposite idea for HO, so less than or equal to 185. So those were our competing pair of hypotheses. There's our claim. And now we're given a bunch of data. This is the data that's required to come up with a test stat for this topic. So X bar is 200 pounds, but we'll just write 200. We'll just use the number. The standard deviation here, they say it's the population value, is 33.3. And then from there, we're going to take those values and plug them into a formula. The formula we're going to use is as follows. It's Z is equal to X bar minus the mean sub 0, right? So mu sub 0, that sub 0 there, that little subscript is indicating where we're going to get the number from. It's going to come from HO. That's why it has the same subscript as HO. Then sigma over the square root of n. So now we plug in the numbers, plug in the values, X bar here being 200. The number that we get for this value is actually going to be 185 because it's telling us with that subscript, get this hypothesized mean from the null hypothesis, which we assume to be true in the beginning. And we're going to take the equality case, the idea that the mean is equal to 185 for this part of the problem. So mu sub 0 is going to be 185. We'll draw a line underneath it, and the standard deviation is 33.3, and the square root of n is the square root of 36. Okay, so that's the formula. I'm going to work that out in a minute and see what it turns out to be. So let's do that here. So I have our calculator up, and I'm going to show you how to do it all at once. You can put the parenthesis here and put 200 minus 185, close that parenthesis up, then divide by, so now a division, open a new parenthesis, put 33.3, and then divide by the square root of 36. Now, of course, you know that that's 6, so it's easier just to type 6, but I want to show you how to do it in case it was a square root you couldn't do in your head. So you hit the square root symbol, then 36, close that square root up, and then close the parenthesis for the denominator of a fraction, and you hit enter, and you get 2.703 approximately, 2.703. Okay, and let's just talk briefly about how to interpret this test stat and see what it's doing. It's basically taking the difference between two values, a value here that comes from the null hypothesis, which is the hypothesis we're testing. So we're taking something that's hypothesized and comparing it against a sample value from the real world, so something that arrives from real data. This is the sample mean. It's supposed to be similar to the population mean. So if we see that these two things are close to one another, the top would be very small. So if they were both 200, for example, we would get 0. So the fact that they're apart means that, there's some difference between what was hypothesized and what we saw in the real world. If your hypothesis is good, what you see in the real world should be very similar. So this is, obviously not the same, so there's a distance. The overall number of the test stat tells you roughly a way to look at that distance, right? With the fact that it's a z-score, we also know that this distance is kind of extreme. So, these numbers are 15 apart, right? So the question is that a big difference or a small difference? Well, after you divide by the standard error here, it tells you that as a z-score, because we know 2.7 is a pretty extreme z-score. It's pretty rare to get that value, which means that this is a pretty extreme distance. 15 pounds here is actually pretty large. So in other words, you're saying that what we saw in the real world and what was hypothesized don't seem to be very close to one another, which means that one of these two things is wrong. Either the data is strange, maybe it was collected improperly, or there's something unique about it that happened randomly. That can happen. Sometimes you get a weird sample. Or the explanation is that the hypothesis is wrong. in general, we like to side with the data because most of the time data collected from the real world should be trusted over somebody's belief or hypothesis. So in this particular case, because we see such an extreme z-score, something close to 3, we would tend to think that the hypothesis here that's saying that it's less than or equal to 185 is wrong. So that's the idea behind the test stat. Here's the calculation and the formula, and from there we'll move on to the next step.